So we're recording, today is the 27th of May. Hard to believe, but it is. I hope you enjoyed the spring because it's almost over. It's hard to believe. Wow. And with temperatures like yesterday, I can believe it. So just real quick, I want to check and make sure everybody's got materials. So everybody at this point has Maple, yes. Yes. And everybody has course pack at this point, yes. Are you saying no, Chris? How dare you?
I didn't get the one that I actually ordered.
Did you get one in the mail?
No.
Okay.
Yeah, I don't know.
You definitely should have. You were signed up for the class early enough where you should have gotten one without having to pay for one. So.
Yeah.
I ordered one. Even though you said we were supposed to pay for, I did it before, and I got the one I ordered, and I never got the free one. So,
Ooh. Well, I don't know what to tell you. I mean, I would love to say, go shake your fist and say, I want my $16 or whatever that course.
No, it's just, I'm just saying that's. I mean, he might have been in the same situation as.
But yeah, you should have received it by now. I would definitely give a call to the bookstore and say, hey, I'm supposed to have a course back by now. In the meantime, of course, you've got access to the PDF, so you can always take a look at that if you need it.
Okay.
Just as a warning, my wife is coming back from picking up the dog who was at daycare, so she may be crazy when she comes back in. So just a warning. How about
your wife or the dog?
I wanted to ask that.
I didn't put any strictures on that, so I have no idea.
Fair enough.
Either way, yes is the answer. So what I want to do right now is take a quick look at problem set 1. So you can pull up the PDF. What were the stumpers? What were the ones that people struggled with? Or was it all pretty straightforward? Didn't have any troubles? I mean, I got some questions from like 2 people, one of which was in the royal we. So I assume there was more persons having trouble with questions, but it's one of those things when students complain, they always come up and they say things like, me and some other students are having a lot of trouble with, that's pretty standard, right? It's kind of like when you go up to customer service and you go, me and some other customers were wondering if you're going to, but legit, I think that there might have been some questions on this one, but I didn't really get a whole lot of emails or text messages or remind notes or anything like that. So how was it?
For the most part, it was good. I feel like the part that we struggled most on was 4.
Yeah.
Number 4? Question 4?
Yeah.
Mm-hmm.
Okay. So which aspect of that gave you trouble? Was it setting up the equation or?
Yeah, for me, it was setting up the differential equation, like trying to just kind of read what it was saying and like, kind of put that into mathematical terms.
Yeah. That's the hardest part of this. And of course, that is the part that Maple cannot do. So Maple can solve all kinds of fancy problems, right? We have these wonderful tools that can do the grind of the math and the algebra and the calculus for us, but translating from English into mathematics and back and forth, the computer can't do that. That's where you become super important. And I don't want to spoil the ending for you, but whatever career you go into, that's going to be the number 1 skill to have, which is being able to do the actual conversion into math or conversion from math. Those of you who are going into engineering, you're not going to have to solve triple integrals on a regular basis. You're just not. But if you don't know how to do it and you don't know how to communicate with the computer about it, that's going to make it really, really tricky. And I say that because, Calc 3 instructor is just walking by behind me. Calc 3 instructor, she's like, what? They don't have to solve triple integrals on a regular basis? No, these are engineers. I mean, getting them to tie their shoes. That's why Velcro was invented, so that engineers wouldn't have to tie their shoes. Okay, anyways, enough of that. I know. Let me change a couple of settings here before we jump into this. And I wanted to real quick share my screen, and I'm just going to share my document camera. And what I wanted to do is take a look at that question number 4, kind of get some context for that. So if you're looking at it already, if you have it up already, that's great. I can't show both that and my document camera. My computer's not that fancy. But it says that a microbial toxin destroys a particular strain. So destroys means what for the rate of change?
It's going down.
Yeah, it's going down. It's negative. Okay. Destroys a particular strain of bacteria at a rate proportional to the product of the number of bacteria and the amount of toxin present. Okay, so it's destroys, that means it's negative. So that means the rate of change is proportional to, so it's going to be K times the number of bacteria and the amount of toxin present, the product of those two things. So N times capital T. And both of these, of course, are functions. N and T are both functions of time. So you could say N of little t and times T of little t, but that's what's going on. If there were no toxin present, the bacteria would simply grow at a rate proportional. So grow means what about my rate of change?
It's an increase or a positive.
Yes, we're talking about positive rate of change, and in formula notation, it would grow at a rate proportional to, so K, some other K, times the number of organisms and number of bacteria. Now, these are not the same K values, right? They're both constants of proportionality, but I don't think that they're the same K value. There's no reason to believe that. So I'll call this K1 and K2. So the rate of change because of destruction is this, the rate of change because of growth is this, and positive means this is going to be plus, this is going to be minus. And so overall, we would say the rate of change of N, the number of bacteria, with respect to time, would just be equal to the growth minus the destruction, or you can do the destroys first. It doesn't really matter what order the terms are in, but it's going to be the growth term minus the decay term, right? And in a way, this is very similar to the kind of analysis that we do later on in some of the work that we're going to do, the input-output diagrams. So when we talk about rate of change being the sum of growth and decay, opposite in sign, this is a really basic equation, but yet knowing this allows me to substitute in and come up with a formula that looks like this. So K1 times N times T, capital T, minus K2 times, oh, did I do it backwards? K1. This is K2. This is K. No, I did it right. I did it right.
I think it's just the signs, or
K1, whatever that is. And then K2 times N. Right?
shouldn't it be positive K2 times N and then negative
Oh,
K1?
yes, yes. And I got ahead of myself. The decay, I did them backwards. I'm such an idiot. I write growth and then I write the decay term underneath. I don't know why. So there's minus, there's plus. Yes. So that's the formula. The question now is, does it make sense, or how do we make sense of it? And really, this is the part B that comes into play here, is what's going on with the units. So if we have an equation, the only way for it to be true is if the units of each term work out. So what are the units for this term right here? Let me get rid of that.
Number over time.
Yeah, it's got to be number of organisms divided by time, whatever units they happen to be. Does it say days or anything like that? I don't think it does. Yeah. So every term has to have units of number of bacteria per time. And of course, this is number of bacteria times toxin level. Capital T is not measured in time. It's whatever the amount of toxin is. So what does K1 have to have as units in order to multiply by those two turkeys and turn out to be number of bacteria per time? So the K1 has to have units of what?
1 over time times the toxin or something.
Yeah, very good. So whatever the heck the units are, it's going to be 1 over time times the toxin level, whatever that happens to be. That's K1. And if I multiply that by number of bacteria times the top with the toxin levels on the bottom, isn't it? 1 over the toxin level. If I multiply that by n times t, the units are going to work out, and I'll have just number of bacteria over time. Right. So, as is the case in a lot of mathematical modeling, we kind of retrofit things. We decide what units these constants have to have in order to make sense of the equation. What about K2? What units does K2 have to have?
Just 1 over time.
Yeah, it's just 1 over time. So they are both constants of proportionality, but they're both fundamentally different in terms of what they represent. This one represents per time per toxin, and whatever that is, and this just happens to represent per time. Right. So number 4, the hardest part, getting it set up, translating, and coming up with that. And I'd love to tell you that there's a system, there's a formula that you can follow to do this. But that's just not the case. Translation is kind of a sticky business. What about other problems that held you up or that you found
How do the
challenging?
first and second terms have the same units though? Because if T is 1 over toxin and N is just number, right?
T is not 1 over toxin. The K1 has units of 1 over time times toxin. So when I multiply this, which has 1 over time times, scooted up, 1 over time times toxin, then when I multiply that by number of bacteria times amount of toxin, the toxin level cancels and I just wind up with bacteria per time.
Okay.
Yeah.
So then the units for N would just be number.
Yeah, number of bacteria. Mm-hmm.
But what would the units for T be then?
Capital T, I don't know. It could be like milliliters of toxin or micrograms of toxin. I don't know.
But it would be in toxin.
Yeah, it would be whatever units of the toxin happens to be. And so I don't think it says in there, and I purposely left kind of super specific units out, but it says the amount of toxin present, capital T of T. So probably it would be in units of like milligrams or milliliters or parts per million. Who knows? I'm not a toxicologist, but I play one on TV. So other questions on the problem set? Or not even questions, other comments about the problem set? Which one was the easiest one? Ooh.
I think 2 was like the easiest mathematically. Just a lot of reading.
I felt like number 5 was the easiest.
Oh, really? Number 5? Okay. Yeah, if you understand the concept of how to find a equilibrium solution, then it's not too bad. Number 2, remind me, which one was that? Oh, yeah, even though it was wordy, you had the formula, you knew the solution, you knew the decay equation, right? So it wasn't too tough to kind of do some sleuthing and work backwards in order to calculate how much time. I think the one part that, and I don't know why this is, I think it's just a definitional thing. The one part that trips people up is if I ask you for an initial value problem, what do you have to give me? What are the 2 things you have to give me if I ask for an initial value problem?
The differential equation.
Got to have a differential equation. Plus?
The initial, what's the name? Initial condition.
Condition, yes. So if I ask you to set up an initial value problem, I'm not asking you to solve it. I'm just asking you, give me a differential equation and give me an initial condition. So for example, if for that first problem, it says, for part A, it says state the initial value problem. If you told me this, or now I guess that would be lambda up there, right?
Yeah.
Oops, R0. What's wrong with saying that is the initial value problem?
Because it's not.
What's wrong with it?
Because
What are the two parts you have to give me?
The initial value.
And
Well, the R of t is not a differential equation.
it's not the differential equation. This is actually the solution for the differential equation, right? And I don't know why that one just uniformly trips a lot of people up. So it's a very common mistake because we're so used to trying to solve everything. But for part one, I wasn't asking you to solve anything. I was just saying, set up the equation. That's not the DE. The DE is this. I think it's lambda, negative lambda technically, times R.
Or not.
Yeah, not R naught. That's just R right there.
Oh, just R.
That's
Okay.
technically it's R of t, right? That's the function. This is saying the rate of change of the amount of stuff is equal to this proportional constant times the amount of stuff at any given time. So as the amount of stuff increases, that means it's going to decay faster, right? It's steeper in the negative direction. As the amount of stuff decreases, gets smaller, that means the rate of change gets less negative. Less negative means, more positive. So you wind up with a curve that we completely expect looks something like that, right? A decay curve. And it's going to cross the axis, but has some initial condition. But
And when we're writing the differential equation part,
Mhm.
Would you rather us keep it like you have it right there, dr dt equals negative lambda times the function, or because like the way I wrote it, I replaced r of t with r naught e to the negative lambda t.
Well, if you're going to do that on this side, then you would have to do it on this side as well, and you'd just be testing. You'd be verifying the solution at that point,
Right.
right? But this right here, this is the way it's written like this, that is the differential equation. If you substitute the solution in on one side, then you have to substitute the solution in on the other. Technically, what we're saying here, this is the same thing as the derivative with respect to time of some function r of t is equal to negative lambda times r of t.
Right. That
Right.
makes sense.
And so if you're going to sub it in over here, then you got to sub it in over there.
Okay.
Yep. Any other questions about problem set one? Kind of weird. I haven't had a chance to really look at them, so I don't know how you did. I'm just kind of operating off of similar questions in the past have caused problems, but I don't know. I'll take your stunned silences. Yeah, it was okay. So we got some practice with unit analysis. We got some practice with the concept of equilibrium solutions where rate of change is equal to 0. You got some practice doing some equation mashing and manipulating, right? But we didn't really do much in the way of solving differential equations, right? You didn't actually go through and find the solution for this thing too much. We just kind of started with the assumption that we knew what the solution was for the exponential decay model. That's where 1.2 comes in. And so 1.2, let me stop sharing here. 1.2 asks the question, so if we wanted to be able to solve a differential equation, what are the different methods that we might use? And the first method that we come across in 1.2 is an analytic method. And of course, the analytic method probably, just out of curiosity, by show of thumbs up or hands, how many of you had seen the separation of variables method before, the analytic method separation of variables? Never seen it before? Okay, a couple people had. So typically that gets kind of just barely covered, just kind of skimmed in Calc 2. It gets mentioned in Calc 2 because Calc 2 is kind of a grab bag course. You're sort of jamming everything in that you didn't get to cover in Calc 1, plus some stuff that you definitely want to cover before you let people off the hook for further calculus, because a lot of people stop at Calc 2. And then those who go on to further calculus, you probably build on some of that stuff. So what I wanted to do, and kind of similar to what we did last time, is take a look at what are the big ideas, what are the key points, if you want to call it that, for 1.2. So the first one is this idea of the analytic solution. And for us, the word analytic solution, That word analytic really just translates to what you and I commonly refer to as by hand, right? So this is by hand. So it's the way that we've learned to solve everything up to this point in our mathematical careers. And if you had a particularly robust mathematical background in a whole bunch of different ways, you might have spent some time learning how to use graphs to solve things, right? Graphical solutions. But deep down inside, we all know that if you solve it by hand, it just feels more satisfying. It's like, that's really the answer, as opposed to a graph solution, which is kind of like sort of an approximation. That's really legitimately what we're doing when we solve things by hand. We're finding exact solutions. And so an analytic solution, what we call the by hand solutions, there's a whole bunch of different methods that we're going to learn. The first method, our first method, is this separation of variables. It's Irish. I don't know why. And so separation of variables says that if you have a differential equation, so imagine you have some dy dt, that's some function of t and y. If it looks like this, if it looks like some g of t times some h of y, then you have a separable differential equation. Now, this is kind of airy-fairy, high in the sky, abstract and theoretical, but really what this is saying is if you have a single term that it can be written as a single term that's a product of something in terms only of the independent variable times something in terms of only the dependent variable, right? So just a reminder, this is only in terms of the independent variable. And this guy right here is only in terms of the dependent variable. So if you can write it as a product of those two things, then it's what we call separable. And this method works like a charm. It's great. You basically cheat a little bit and treat these two differentials as if they're kind of their own separate entities. You separate them. You like multiply both sides by dt, divide both sides by h of y, move that over here, and then you integrate both sides, right? It's technically cheating, but it works out as long as it's a separable differential equation. So let me give you an example of one that is and an example of one that isn't, just as a reminder. So for example, if we had dy dt equals 2y plus y squared times, no, that's it. I'll just do 2y plus y squared. It's technically two terms on the right-hand side, but you should be able to see that this whole thing right here is one big function of y, right? This thing right here, this whole thing is h of y. And so if that's h of y, then what the hell is g of t? Where's the function of t? What do we do?
Multiplying everything by t to the 0.
Yeah, it really is there. It's sitting there. It's times, all this is times t to the 0 power, or just 1 if you want to think of it that way. And there's your function of t. So there's your g of t. So the nice thing about this trick is you can always multiply by 1. So you can always, if it's a g of t, that's you don't see it, it's there, it's just times 1. Or if it's maybe the h of y, it's there, you just don't see it, it's just 1. And so this method works. So that's an example of one that you could use the separation of variables to solve. Turns out it'd be a little bit of a pain in the ass to write it as a solution y of t equals, but you could try. Just for giggles, right now, would you ask Maple to solve that differential equation? As written, dy dt equals 2y plus y squared. Good practice, type it in, see if you can get Maple to solve it. And while you do that, I'm going to write down another one here. Now, who's brave enough to share their screen and show us what they got when they asked Maple to solve that differential equation? Even if, especially if you didn't get it or you couldn't get Maple to do it, we can diagnose the problem together. But go ahead and share the screen. See what you got.
I'll go.
Yay! You're my hero, Wyatt.
All right. So
Aha! So Wyatt typed in dy dt equals 2y plus y squared. Now, first problem, what kind of solving do we want this thing to do?
we wanted to take the to take the derivative, so we need a different operator.
You need a desolve in there. Not just solve, but a desolve. Yep. And then the second problem is you have dy dt, and so you're telling the computer that y is a function of t.
Mm-hmm.
But we need to be able to explain that dy dt, that y actually is a function of t, both on the left-hand side and the right-hand side. So we're going to need to tell it, take the derivative of not just y, but take the derivative of y of t. So go back into your code there, inside that differential on the left side. Yeah, okay. Yeah, you got to do it on both sides, so go ahead.
Oh, dy of t at the top? Okay.
Yep. So y of t up there. And go ahead and put parentheses around it just in case, because I think, did you just type in dy over dt, or did you use the palette?
I just typed in dy over dt.
Yeah, so you're gonna want to. I don't know if it's gonna like that. Let's see what happens. Now go ahead and what you had before, put that in as 2 times y of t.
Okay.
Mm-hmm.
And then should I do 2 y squared of t?
It's going to be y of t, and then the squared will go on the outside. So yep,
okay.
Just like that. Now go ahead and hit enter. Let's see. Okay. So yeah, so it's not sure what to make of your differential on the left side. So go ahead and erase that, and then find in your calculus palette your derivative there. Mm-hmm. And so on the bottom, oh, no, don't change that. And then in the bottom, you're going to change that to a t. And then hit tab. And then yep. And then just in parentheses, y of t right there.
Right
here. Mm-hmm. I don't know if it's going to like it. Let's see. Hey, look at that. So Maple can solve it. And so can we, if we apply the separation of variables method. It's not terribly tricky. It just takes a little bit of patience. And while I've got you up and doing that one, let's try another one. Let's do a desolve. And then parentheses. And then this time I'm going to have you enter the code for it. Type diff, D-I-F-F, and then open parentheses. Y of t, comma, t. Close parentheses. So what you just typed right there, that's equivalent to dy dt, right? So you're taking the derivative of y of t with respect to t. And then that's going to be equal to 2 times y of t plus t squared. Yep. Now, this thing is not separable because those two terms are of separate functions. We don't have g of t times h of y. We have g of t plus h of y. So we can't use the separation of variables method, but yet it still is solvable. So what I'm just pointing out is there are methods that you can use to solve differential equations beyond separation of variables. It's just the first one that you'll learn, but it's not the only one. There's literally hundreds of methods for solving differential equations, and no single one of them works every time. It's kind of like, I don't know if you guys remember when you first learned how to solve algebraic equations, and it was always like x plus 2 equals 4, and you're like, this is easy, and all of the examples you see are the same, and then somebody goes x squared plus 2 equals 4, and you're like, what the hell is that, right? And you're like, I've never seen that before. You can get it to x squared equals something, but then how do you get rid of that squared? And you're like, oh, well, this is a different kind of equation. We need a different kind of tool. It's the same thing with differential equations. Certain types of equations have certain methods that can be used to solve them. Separable differential equations can all be used, or can all use the same method to solve them. So the other thing that we learned in 1.2, thanks by the way for sharing your screen there, Wyatt, appreciate it. The other thing that we learned in 1.2 was a little bit about the types of applications that we might run into. So you watched the video about the mixing problem, right? And so the inputs and the outputs and modeling the mixing problem. Usually the tough part that people run into with the mixing problem is that they forget that the differential equation represents a rate. And so every term in that equation has to be a rate. And so it's the amount of substance per time. And so whatever units you kind of stack together, when they multiply together for each term, they have to fall out to be amount of stuff per time. And so that takes a little getting used to. But what I thought we could do right now is turn our attention towards the classwork for 1.2. And I'm going to give you guys a chance in teams here. Who are we missing? We've got, who are we missing? From what team do we have somebody missing? Bryce is here. Emma's here, Austin's here, Matthew's here, Stephen's here, John's here, Quentin's here, Wyatt's here, Paul's here, Anthony's here. Is everybody here? 8, 9, yeah, of course, because with me, that makes 11. Duh, I'm such a fool. Okay, so what we're going to do is I'm going to have you guys split into your team rooms. I just got to get the breakout rooms up and running here. We're going to go 3 rooms, and breakout room number 1 is going to be Anthony, or Chris, as he's sometimes called, Paul, Wyatt, and Quentin. Sorry, this is thrilling that you get to watch me do this, but I can't talk and do this at the same time. So Matthew, Stephen, John. Okay, and then last but not least, so I assume that you have caught on, those of you who were in Team Phi and Team Q, you caught on that we lost 2 folks. They didn't come back after the first class, so I assume that they're not with us anymore. I haven't heard from them. I hope everything's okay, but I'm pretty sure they dropped the class. So have you guys heard from them? Did you guys get word? Rest in peace. Yeah. Did those of you in Team Phi or Team Q, did you get a note from anybody saying, we dropped it? No? Okay, well, you know what? To heck with them. Anyways, I'm going to give you the rooms now. You're going to be working on your particular problems. Get started, and I'll pop in and check on you. Recording. So we're going to take a look at the classwork exercises now, and each person or each team worked on a couple of them. So we'll have Team Diff start off and show us what you got for example 1 or exercise 1. And if you want, you can share screen. If you've got something typed in, you can do that.
I guess I can take that one.
Oh yeah, and this is actually nice because Paul was typing his work into Maple, which is, I think, a really handy thing to do. There's all kinds of reasons for doing your homework in Maple. Number 1, you get to save it, and you can like print it. You can actually edit it, unlike what you can do with handwritten work. It's nice, and you have it forever, right? It's electronic. It's all kinds of good reasons. Anyways, what you got, Paul?
Okay, so it said to find the general solution of the differential equation dy dt equals negative 2y. So I took dy divided by the negative 2y and took the integral, or well, put the integral sign in front of that, equals the integral of dt. and then I took the integral of both sides, which gave us -1/2 ln y, ln absolute value y, plus c1 equals t plus c2.
Nice.
And then, let's see, what did then I shifted the c1 over and made c2 plus minus c1 equals c3. So then ln absolute value y equals -2t plus, oh wait, what did I do? Oh yeah, divided by the -1/2. So ln absolute value y equals -2t plus c3.
Now, technically, it's no longer C3 though, right?
Oh yeah, so it should be c4. I did that
Yeah.
next.
And that's okay. You could, if you wanted to, do those two steps at once. I would not lose my cool if I came across that, because I think you guys are good enough at math where you can do 2 steps of simplification at once. I'm okay with that.
Anthony caught that. Okay, so then I put y, then I took, let's see, so then I took the exponential for both sides. So it was y equals c4 e to the -2t, which I think is the answer.
Yeah. Yeah. And of course, you can verify that. You could ask Maple to solve it for you, and you could find out that that's exactly what Maple would say the solution is. Or, as you did, you can verify by substituting it back in. And I cannot stress to you how important, not you, Paul, but you, everybody, how important this idea of how do you verify a solution. You put it back in the equation, but not just on the right-hand side. You put it everywhere that the function, everywhere that the solution, in this case, y of t, appears, you have to put that solution value in. And so when he did that, he asked the question, does the derivative of the solution equal -2 times the solution? And the answer, of course, is yeah, because when you take the derivative of c4 times e to the -2t, you get 2 times c4 e to the -2t. I don't know where the constant upstairs came from.
That's, which one?
I think you turned your C3 upstairs, or your
Oh,
C4
was-
downstairs into the C3 upstairs.
That was
Oh,
because originally
From
we
previous.
didn't have it, like we didn't bring the constant down.
Mhm.
So that was from before we did
Yep.
that.
And that would be another way of writing the solution that's perfectly valid. It's just a little clunky, right? To have the constant in the exponent, it's a little clunky. So instead putting the, yeah, exactly, the C4 out front, and then it just becomes that. Very good. Well done. Sometimes the one step that trips people up is that step just before you get your answer, where it's natural log of the absolute value of y equals some stuff. The step to go from there to the line below, that exponentiation step, it's actually a little bit tricky. The first time you see it, or the first couple of times you see it, you're like, whoa, wait a minute, how did I do that? But e to the power natural log of stuff is just stuff, right? The e to the power of natural log cancels. But here's the catch, and this is maybe for some of you a blowback or a throwback to pre-calc. If it's e to the power 2 times the natural log of stuff, it doesn't work. It can only work if it's e to the power of natural log with no coefficient, or a coefficient of 1 in front of the natural log. So keep that in mind. That's going to come back to bite us later on in chapter 1. So nice work on number 1. Excellent. Okay, who wants to help us out with number 2? Team Fee, you got a big number 2 there.
I will represent us.
Okay.
So let me share the screen.
Ooh.
I know, fancy. 21st century, it's pretty amazing. Okay, so question 2 was, we're using the separation of variables technique to solve all these 3. And so that's more or less what we did. So for part A, we had our equation, and then we did some fancy stuff, and then we took the integrals, which was here, and then we did more fancy stuff, and we isolated the expression for x and got e to the -1/2 t squared plus c4, which, yeah. And then here's our C tracker, if you'd like to look at that stuff. That's all very fancy. And then for B, we did pretty much the same thing, except we divvied up all the work. So I don't have all the work on this exact document, but there it is. And I trust my teammates, so I'm going to say it's right. And for C, we prioritize
so-
question 4.
Real quick, for part B, that's not an equation. That's just an expression. So is that equal to something?
You know, that's a good question. I'm going to assume it's equal to y. Would be the most reasonable thing. But do you have any comments on that, teammates of mine?
Y of t.
Y of t? Yeah.
Yeah.
Okay. So here's a question. What if somebody said, I don't know if I believe it. How could you verify that that really is the solution, the general solution?
You know, you just
Put it in Maple.
say, yeah, you put it in Maple.
Well, what does that mean though? Put it into Maple. You got Maple document right there. So if you
Yeah.
click over to math on that line, what's the code you type in to actually take the derivative or take the solve the differential equation? Dy dt equals 2 minus y. That's what this equation is.
D solve parenthesis.
Oh, look at him copying and pasting. Sneaky devil. So I will tell you, copy and paste is a wonderful thing. One more parenthesis, there you go. Copy and paste is a wonderful thing, but in terms of learning the code, it sometimes is a little dangerous to do copy and paste because you'll get so used to just go grab this and you never really learn what the code is to type in a differential equation. And you got to practice. So let's see, what did Maple come up with? It came up with 2 plus e to the negative t times a constant. And you came up with 2t plus or minus 2 plus e to the negative t plus a constant. The plot thickens. So it seems to agree with you if you pull that constant, you know, because e to the negative t plus a constant up there, you can turn that into e to the negative t times e to a constant, which is itself just a constant.
Mm-hmm.
So that tends to agree with you. But the other two terms that you have, Maple says only the 2 is there, and it's not negative, it's positive.
Yeah.
So we'll have to go back and check our work for that one. Okay, so what about C? What'd you do for C?
So C, we'd actually popped down to question 4 and tackled that one real quick and then came back to C. So we were a little bit out of time, and by a little bit out of time, I mean, I did this in 30 seconds before I got kicked out. So what we did was we factored out the 1 over b cubed, sorry. I'm gonna zoom in over here so you guys can see that. So you see this little blurry stuff, little 1 over 3 cubed.
Mm-hmm.
And then we said, hey, that's one function. So we multiplied it over, we did all the fancy manipulation stuff. Then we took the integral of b cubed with respect to db and set equal to the integral of r squared plus 1 over r dr. And then Maple said, this is the answer to that. And then so we said, okay, let's isolate it for b. And then
it's missing
we got to
the
read out.
constant. The only trouble with Maple when it does indefinite integration, it doesn't write the constants in. It's really weird, and I don't know exactly why. I'm sure there's a good reason for it, but off the top of my head, I don't know what it is. So b to the 4th over 4 plus a constant, and the other side would be r squared over 2 plus the natural log of r plus a constant. You could combine them if you want, but. And then the trouble with this, of course, is you're solving for which variable? Which is your dependent variable that you're solving for in this case?
It's b.
B. So you have to take the 3rd root of, or sorry, the 4th root of a whole bunch of stuff. And so that's what the root of is telling you. So it's kind of a mess,
Okay.
but you're taking the 4th root of that.
Is the z to the 4th the constant?
No, the z to the 4th is not the constant. The z to the 4th is telling you you're taking the 4th root of, and then all that other stuff is after you've kind of solved it for b. So making
so
sense
the 4th root of this stuff right here.
Yeah, the other junk on that side.
Not necessarily so,
yeah, all that. It's basically what would happen if you moved the b to the fourth. You multiply by 4, and then you move the b to the fourth to the other side and had the whole equation equal 0. Right? So it'd be b to the fourth. Everything else moved to the other side would be b to the fourth minus 2r squared minus 4 natural log r. And so that's what it's telling you. It's not actually finding the fourth root of all that. It's just writing it in code. For us, we would say b is the fourth root of some stuff. So it's a little clunky.
All right.
So real quick, because you've done this in the past with stuff that you've shown on the screen, and I want to point out to people because they may not recognize it. So if you scroll up, you've listed question 2, and then there's like a drop-down menu. And if you click on that arrow, you can actually close it. Does anybody else know how to do that? Stunned silence. So I'm going to take that as a no. So Stephen, how did you do that? That's so cool.
Well, I've been doing it the annoying way. 'Cause I've been wanting to. It's up here. I can't get my mouse up there
Oh,
because of
just
the
push
little-
harder.
Well, there's
I'm
a
joking.
little menu thing that says it keeps popping down saying I'm speaking and I can mute myself. I can
Oh,
like
got it.
grab this or something.
Is it
there we go.
under, it's under
There we go.
insert?
It's this one right here. So this button right here. I don't know if you can see my mouse. That's it.
Yeah.
I don't know the command for it, which is annoying me, like keyboard command.
Control
Because-
period.
Is it?
Control period. Should work.
It's not working for me.
Yeah.
I have a Mac, so it wasn't.
Oh, maybe it's, so it'd be command period, I guess?
I'm trying command period, but it's not.
I don't know what it is on Mac, honestly. For a PC, it's control period, and it creates basically a drop down, so you can like list everything and you can collapse. It's collapsible, basically. It's inserting a collapsible section. That's what it's called.
Is
So
it
on
called
mine,
section?
it's called section.
All right, I'm gonna Google that later.
Yeah.
Ooh, I did
So,
something.
yeah, that's something. So those of you who are getting used to using Maple Docs, that's one of the nice things that you can do. You can kind of keep everything tidy. You can do question 1, 2, 3, 4, 5, and then open them to create and edit, and then collapse. And it's still referable. So you can like name a variable inside one of them, collapse it, and it will be referable later on in the document. So it's pretty handy to do. Okay, so that gets us through number 2. Number 3 was considering the differential equation. For what function g of x will this equation have a particular solution? Blah. Who wants to take this one?
So Austin was going to, but I think his Wi-Fi cut out, so I will.
It's Wi-Fi cut out.
That's what. So I'm assuming.
Got cold feet.
Okay, happens to the best of us.
Actually, I'm gonna keep it like that. So
Can you
right
bump
here.
up the view? Go into view and then do zoom. A little bit further down. Zoom factor.
I'm not seeing it. Oh, right here, right here.
Yep. And then 150 should be pretty good. It just makes it easier for everybody to see.
If you
that
hold
better?
control, you can use your mouse wheel to scroll in and out.
That's true too.
Oh, fancy. So it was. I was kind of struggling how to show this. But basically, we were saying that y of x is e to the 4x. So then we just plugged in e to the 4x where y to the x would have been, which is here and here. And then I showed that on the left side, we're taking the derivative of e to the 4x. That gets us 4 to the e to the 4x. And then we said basically here, in order to make this function the same as this function, or sorry, this function, e would have g of x would have to be negative 2x.
It's the only way you can make the left side of the differential equation equal the right side when you substitute the solution in.
Correct.
Yeah. Nice. Yeah, I'd say the only thing you might want to do, for clarity's sake, is at the top, just above your first line of work, say, I'm going to substitute the given solution into the differential equation.
Okay.
You know, just to kind of say, this is what I'm doing. Otherwise, it's sort of like plop down some work. It's like, where'd that come from? What's this about?
Yeah.
Yeah.
Yep.
Cool, cool. Nicely done. Okay. Let's see. That's number 3. We're gonna skip over number 4 only because number 4 is actually, you know what? We're not. Number 4. Do you guys have it in Maple? Did you do it in Maple?
We did, yes.
Can you show real quick just a reminder of how we solve an initial value problem in Maple? Just in terms of the code. And I don't know if you've caught on, but you have to learn how to do this stuff in Maple. So having your own document open and throwing stuff in there and being like, oh yeah, I got to remember this for later. Here's the code. Here's the structure for how to solve things in Maple. Okay, so what do we got?
I just typed out the equation that we got from part A.
Oh, okay.
Which was here.
Got it.
And then with the C.
Got it.
And then I plugged in I said equal to our X. Oh, it just disappeared. What did I do? Oh, I closed it. So I set it equal to 1 over square root of pi, and then I set the t equal to 0, and then I just told it to isolate the expression for C4, and then it did. And then down here I made it give me the decimal.
An approximation, yeah, that's good. So underneath that approximation, can you add one more line of code? And for this code, let's have it do the desolve and actually solve it with the initial condition all at the same time. So parentheses, and then we're actually going to do curly brackets inside that.
All right.
And so let's type in the original differential equation, which, if I can remember.
The mouse is not cooperating for some reason.
It's okay. The differential equation is, you can just type in diff, then parentheses, x of t comma t equals, and the right-hand side was negative x of t times t. And then comma, we're still inside the squiggly brackets, and now we're going to type in our initial condition, which was, it would be x of 0 equals 1 over pi.
1 over the square root of pi, though, right?
Yeah, 1 over square root of pi. Yep, very good.
Okay.
And then close curly brackets, and then close your parentheses. And so this is the code structure for, I want to do a desolve all at one time. And notice, that's what you get. Now you might be looking at it and thinking, hey, wait a minute, is that the same thing as?
That didn't help.
So what happened?
It didn't like the E or something. I don't know. If I like copy and paste and get rid of the X of T stuff. Nope.
So what are the possible explanations for this at this point? We got a different value for what should be the same constant, C4.
It's not evaluating T at 0 for some reason. Because T should be 0, right?
Well, keep in mind, it's basically solving the differential equation, getting the general solution, and then substituting in the initial condition to find that value of C. So it's doing.
So it's not even trying to give a constant in the first place.
No, it does it all in one step. So that is the answer. That is the particular solution. Let me switch over to my screen real quick. And I want to show you on my doc cam kind of what this would look like, what this solution would look like if we did this kind of by hand, writing it out. So we have dx dt equals negative x times t, right? And this is definitely a separable differential equation. So I'm going to move my x's to one side and my t's to one side, and I'll wind up with dx over x equals dt, negative t dt, right? And I'm going to integrate both sides. And so this side is just natural log of the absolute value of x. And this side is just going to be negative t squared over 2. And I'm going to add the two constants together and scooch them over there and call it C1. Now I have to exponentiate to get rid of that natural log. And so if I think about raising each side as the power of e, then I wind up with absolute value of x equals e to all this junk up here, negative t squared over 2 plus C1. And that's all upstairs. And the good news is I'm talking about the absolute value of x, where x, we're only interested in the positive values, but e to any power, any real number power, is guaranteed to be positive no matter what. So I don't actually need the absolute values there. So I just write this as x of t. And then over here I've got e to this stuff plus a constant. So I can think of this as e to the C1 power times e to the negative t squared over 2. And this thing right here is just a constant. So I'll rename it as C2 or C4 or whatever you want to call it, right? E to the negative t squared over 2. So is this the particular solution that you came up with? Or sorry, is that the general solution you came up with? Sorry.
I was muted.
Oh, sorry.
I don't think so, not according to Maple.
So that might be the problem. That might be the problem, is that this is the particular solution, or the general solution. And now if I want to find the particular solution using my initial condition.
Oh, no, that is what we got.
Is? Okay.
Never mind. I was looking at the particular solution, not the general.
Okay. And so if I plug in this initial condition, I can figure out what C2 must be equal to. So x of 0 is 1 over pi, square root of pi, sorry. And that's going to be equal to C2 times e to all this stuff is just to the 0 power. And anything to the 0 power is just going to be 1. So C2 is equal to 1 over the square root of pi, not 1 over the square root of pi minus 1. So I think there might be a breakdown when you were solving for C2, right? This is telling me that C2 is equal to 1 over the square root of pi. So if you switch back to, let me stop mine here. If we switch back over to, oh, by the way, and so the end result would be the 3 dots means, okay, this is the solution to the problem. The overall particular solution is, there's my constant, 1 over the square root of pi, times e to the minus t squared over 2. This is the particular solution. This right here, that's the general solution. Right? You throw any constant in front of that, you'll get a particular solution. One particular solution happens to be where the constant is 1 over the square root of pi. So what I want to do real quick, Stephen, is let's take a look at your Maple document and see what you were typing and see if we can figure out where it went sideways.
I got lost in my C's, I think. And I added a C at the end of here. I added a C4.
Instead of upstairs, it should have been upstairs in the exponent.
Yeah.
That's why.
Yeah.
Yep. Yeah, that was the problem. Yay. It's always nice when you can figure out what happened. The postmortem is incredibly important. Okay, so that gets us through, let's see, what problem was that? That was number 4. Number 5 and number 6. Number 5 is kind of a wordy problem. It's a concept problem. So can you talk us through for number 5? We'll skip A for right now. I'm particularly interested in your answers for part B and part C.
I think Austin was going to talk about that again, and he left on accident.
On
We just
accident. It's like, oh shit, he's gonna make me talk. Gotta go downstairs.
We just looked at page 12 in the notes. I don't know if Emma had a better explanation for this one.
Yeah, I was gonna say I can talk. So for part B, the every separable differential equation is autonomous. First, we kind of just wanted to establish like what autonomous meant, which obviously was in the notes. So it says that the right-hand side depends only on the dependent variable and not on t.
Or the independent variable, whatever it happens to be.
Sure. And then essentially we used page 12, and the example that we have was non-autonomous, yet it was separable, and we were able to solve it that way. So that was a perfect example of why that part B is false.
Okay, so let me pull my document camera up here one more time, and give me an example of something that is separable but not autonomous.
I just used your example. Is that okay?
That's fine. Whatever it is, sure.
dy dt equals t over y.
Okay. Separable?
Yes.
Yeah, because this is really the same thing as t times 1 over y. So you've got a function of the independent variable times a function of the dependent variable. So you could separate them, move the y to the other side, move the dt to the other side. It works fine. This is totally separable. But is it autonomous? You say no. Why?
Because it is, because it has two variables. It has the t and the y on that side, on the right-hand side.
If the right-hand side has more than the dependent variable going on, then it doesn't count. Then it doesn't count as autonomous. So we found one that is separable, but not autonomous. How about the other way? Is it possible to have something that's autonomous that's not separable?
Is that kind of going into part C?
Yeah.
Okay. Part C, we said that was true because even if there is only just the dependent variable on the right-hand side, you can always multiply by 1. As
so even if you have an autonomous differential equation, which looks like this, right? So right-hand side is just a function of the dependent variable. You can always think of it as times 1, where this thing is really a function of the dependent, or the function of the independent variable. So in this case, this is separable and it's autonomous. But I'm going to turn your attention back to the question, because the question said true or false. Every separable equation is autonomous. Every separable equation is autonomous. Well, we proved that can't be true right here.
Yep.
So that's got to be false.
Yep.
But for part C, every autonomous differential equation is separable. You think the answer to that is?
True.
True. And your argument is if it's autonomous,
yep,
it's right. It's like this. You can always multiply it by 1, and that's a stand-in dummy function of the independent variable.
Exactly.
So, nicely put. Well done. That's a great example of one of those questions that Maple is absolutely no help answering, right? You can't type it in an answer. You have to know the definitions. You have to understand the relationship between the concepts. So good job. Last question is a bit of a doozy, but it's named after a candy company, very famous candy company. Paul, you want to share your document?
Sure. Let me see here.
Hey, Austin, you don't have to talk anymore, so don't worry. You don't have to have internet trouble anymore.
He conveniently shows back.
Oh, look who came back.
It's computer trouble, not internet trouble.
Well, good. I'm glad to have you back, but sorry you missed it.
Okay, well, it says that the candy company uses a large mixing tank that initially contains a mixture of 450 gallons of water and 50 pounds of sugar. And more sugar water is added at the rate of 5 gallons a minute, with 2 pounds of sugar in each gallon. And a well-mixed solution of sugar water is withdrawn at the rate of 5 gallons per minute. So here, I'm going to get my drawing.
So we learned we can do drawings in Maple. It's exciting, and it make you feel like a 2-year-old with his crayon, like. Right?
Yeah, I actually had a better pencil drawing, so I'm going to share that one.
Yeah, drawing with a mouse is never easy.
Yeah, I found that out. Okay, there it is. So there was 2 pounds per gallon going in at the rate of 5 gallons a minute, and 5 gallons a minute going out.
So you have 2 pieces of information for the input, but only 1 piece of information for the output. Okay, that's what we're given. That's the information we're given to begin with.
So that was A. Okay. Now for part B, try and create a differential equation model to find the amount of sugar in the tank at each time. So this is what I did, where we did. The dA over dt equals 2 pounds per gallon times 5 gallons a minute, minus 5 gallons a minute times the A of t over 100 pounds per gallon.
Okay, can you stop right there real quick? Can you explain? I mean, I got the 2 pounds per gallon and the 5 gallons per minute. That's your input information. The 5 gallons per minute, that's the output information. Where did the other parenthetical factor come from? The A of t over 100. Where'd you get that?
Actually, I was just following your example, and I'm not really sure. Oh, wait, that should be 450.
Yes, it should.
Oh, wait. 50.
Nope. You had it right. It was just 450. Yeah, so what you're doing there is you're saying whatever's coming out of the tank, it's flowing at 5 gallons per minute. That's given to us in the problem. The question is, I need to multiply that by pounds per gallon in order for it to work out. The question is, how many pounds per gallon of sugar are there in the tank that's flowing out? And the answer is, I don't know. It depends on how long the machine's been running. It depends on how much sugar's been going in. It is literally a function of time, A of t. It's, I don't know how many pounds, depends on time, divided by how much liquid is there in the tank at any given moment. And because we know input rate and output rate in gallons per minute, they're the same. 5 gallons per minute go in, 5 gallons per minute go out. What does that tell me about the number of gallons in the tank at any given moment?
Stays the same.
Yeah, it stays the same. It doesn't change. Input flow rate, output flow rate's the same. So whatever was in there to begin with in terms of gallons, that's got to be how much is in there at any moment. And so that last factor is how much sugar in pounds divided by 450 gallons. That represents, literally, that represents the concentration in the tank at any given moment.
So for the, once we get to the point when there's a different inflow and outflow rate, it's going to be another equation in that denominator,
It could be, yes. It could be 450 plus 2t if you're gaining gallons every minute, gaining 2 gallons every minute. Right? That means your flow rate in is higher than your flow rate out. Or it might go the other way, right? You might have a lower flow rate in than a flow rate out. And you can think about this in terms of sugar in a vat, which is probably the easiest kind of simple situation to wrap your head around. But this also matters for things like, you know, I'm looking outside, watching the water drain off my driveway and into the storm sewer that's outside, right? So I can think about that storm sewer filling up from water flowing in, and it can only send out water at such a rate, right? So I could think about the concentration of pesticides in the sewer outside my house. How much is flowing off my driveway? I don't use pesticides, so none. Excuse me. Minus how much is flowing out of the sewer later on. So this works as a metaphor for a mixing tank if you're talking about sugar or salt, or it could be hot sauce in a pot. It could be anything. These mixing problems, we should be able to kind of export this model and use this in other places. So the other thing that I want to point out, and Paul, you did a lovely job, really, really lovely job with this, is showing how the units work. Because if you track each one of those terms is a multiplication of two rates. And what do the overall units turn out to be when we do the cancellation of units?
Pounds per minute.
Yeah, which is exactly what we had expected to be on the left-hand side of the equation if we're looking at dA dt. It's the amount of change in the pounds, A, of sugar divided by the change in the time, minutes. So well done. Nice job. And so the setup is the hard part. After that, it's really just a matter of letting the grind of the mathematics take over. Use that separation of variables technique and dump. And after some effort, you can solve this thing. The good news is that Maple can do the solution for us. That equation that you typed in right there, Maple can solve that for us like this. We just have to know how to tell it to do that. So you scroll down to the bottom. Let's see what you come up with for an answer there.
I got AT is equal to C5 e to the minus 1/20th t plus 100.
Plus 200? Yep.
No, I
200.
got 200.
Yep. So that equation right there is the general solution. If you know an initial condition, you can figure out what that C3 is equal to. But it depends on how much sugar you start with in the tank, right? So what is A of 0? That's the real question here. And so you scroll down and you say, hey, we read in the problem that it starts off with how much sugar in the tank?
50 pounds.
50 pounds. Now notice that 450 is important. It's important in the equation. It's not the initial condition. That's how much water, how much liquid is in the tank. And it doesn't change. So nice. So you came up with a solution for A of t. And then, of course, what does that let us do? What does that let us predict? Well, anything. You can find out how much sugar is in the solution at any given moment. 10 minutes after it starts pumping, 1,000 minutes after it starts pumping. That equation you can use to figure out how much is going to be in there. And so you plotted it. Oh, I want to see what it turned out to be. Yeah. So what is it? Yeah, so how would you describe what's happening to the amount of sugar in the tank? Now you switched variables on me. You started using X and Y. You didn't have to. You could use T and A if you wanted to. But if there's too much T and A in your life, I completely understand.
That was just happened to be what I punched in just out of.
That's okay.
Yeah. So it says it'll reach equilibrium when there's 200 gallons of sugar. Oh, should be pounds, not gallons. Pounds of sugar.
Yeah, of course, we have to keep track of the units. That vertical axis is pounds of sugar, and the horizontal axis is time, right? And so remember, Maple is completely agnostic to whatever variables you want to use. You want to call it Francis, call it Francis. You want to call it A, you want to call it T, you can call it whatever you want, as long as you're consistent. And so that graph right there tells us something is happening, and you should be able to see that same thing in the actual equation. So can you scroll up real quick to the A of t equation, the final answer for part E? Yeah. So take a look at that. What would happen if we let t get really, really big?
The answer would go to 200. Right?
Because
that's when it reaches equilibrium.
Well, yeah, but why, in terms of the equation, what's the evidence in the equation that that's going to happen?
Because this top would eventually go to a really big negative number. So e to a really big negative number is just 0.
It's 0. So that whole term just disappears. And in other words, we're making a limit argument. We're saying the limit of A of t as t approaches infinity is just 200. You can see it in the equation. You can see it in the plot of the equation. Just it appears slightly differently. You have to know how to look for it. but nicely done. That's a good example of kind of a big picture mixing tank problem. And for section 1.2, that's kind of the pinnacle, because you have to use separation of variables, but you have to set up the equation first. And you have to understand how to find a particular solution. And you have to understand what the solution means. You have to understand what equilibrium solution means. There's a lot going on in that one problem. So nice work on that. Cool, cool. So that was a lot. We only have a couple minutes left, but what I'd like to do right now is take just a couple of minutes, give you guys a couple of minutes to take a look at the next problem set that you've got coming up, as well as, and you can see that on the agenda for today, down underneath the homework, the problem set 3 is coming due, and that's due next Wednesday. Did I say Wednesday? Wait a minute. Problem set 2 is due on Monday. Problem set 3 is due on Wednesday. And you've also got problem set 4 due the following Monday after that. At the same time, you also have an investigation that uses Maple, that's all about kind of equilibrium solutions and logistic curves. It's relatively short. It won't take you tons and tons of time, and it's pretty prescriptive, but it's getting you using Maple. So my advice would be start working on these things right now. So what I want to do is give you a couple minutes to take a look at in your teams, to take a look at problem set 2, get started on that if you haven't already, but also sneak a peek at investigation 1. This is probably the first time that you've seen it. It's posted on the assignments page as well, but I want you to take a look at these two. Just talk it through. You can even start trying to set some things up, but see if you can talk them through. Problem set 2 is about section 1 and section 2, so there's nothing new under the sun there, but use what we did in the classwork and see if you can spot some valuable places to go. So I'm going to open up the rooms. I'm going to give you about 10 minutes. Give us a couple of minutes at the end to kind of pull back together, and we'll talk about what to do next. Okay? Thumbs up. Austin, very good. Matthew, thumbs up. Yay, he's not in the bathroom. Awesome. Okay, cool. I'm going to open up the breakout rooms. Go to it.